So we're starting off second semester, and we're going to talk about general polynomials. We've talked at length about the quadratic polynomial, but we're going to talk in more general terms from here on out. We're going to talk about larger degree polynomials, and there's going to be a lot of vocabulary today, so hang with me. Get my tablet working, and we're on our way. So this chart looks really intimidating. It's just a way to generalize something in math, and generally when we generalize things, they look even more complicated than just seeing some examples. So here's some vocabulary we have to remember. A degree, and maybe you don't remember this, but a degree is the largest exponent that you see. So if you have x to the second power, that's a degree 2, which according to this chart we know is a quadratic. And then this is the part of the chart that you probably don't want to look at. This is the general form of all these polynomials, and actually this actually has a lot of typos in it. Like all these n's are supposed to be x's, so you know what, I don't even want to look at that. Ignore it. What I need you to know is that if it's a degree 0, we call that a constant. An example of a constant function would be like y equals 3. So technically it's 3 times x to the 0 power, but because anything to the 0 power is really just a 1, we never would write 0 power, we just write y equals 3. A degree 1, called a linear function, an example of that would be, switch colors so it's easier to see, y equals 3x, where it's x to the first power, that would create a line, thus the name linear function. And then our friend the quadratic, an example of that would be y equals 3 times x to the second power. Of course there can be more terms, I'm just giving you really small versions of them, and that's okay. So you guessed it, a cubic would be 3x to the third power, could have some other terms after it. Quartic would be a degree 4, which would look like y equals 3 times x to the fourth power. The 3, I just made that up as a coefficient. It doesn't have to have that coefficient. Quintic, degree 5, would be, I think you know what it's going to be, 3x to the fifth power. And then after that, they stopped naming them, frankly, and they just said, you know what, forget the names, degree 6, degree 7, degree 8. That's all we're going to refer to higher level polynomials. And in Algebra 2, we're not really going to see anything beyond quartic or even a quintic. Primarily, we're going to talk about cubic functions in this year. So the next vocab term we want to have is it in standard form? It has to go in decreasing exponential order. So this is the quadratic term. Here's a quartic term, and then the constant. So it is not in standard form. In order for this to be written in standard form, we'd have to rearrange it so the negative 3x to the fourth term was first, and then we have the plus 1/2 x squared minus 7. So the degree, remember, is the largest exponent, so this is a degree 4. The type is, because it's a degree 4, we call that a quartic. And the lead coefficient is the number that's in front of your lead term when it's written in standard form. So in this particular case, it's a negative 3. All right, our next formula, 2x to the third plus 4x squared, that is already in standard form. So let's keep my colors consistent. I'm just going to rewrite it over here, or if you're really lazy, you just do that. And then our degree is the highest exponent that we see in this problem. So this is a degree 3. Because it's a degree 3, the name for a degree 3 is called a cubic. And then the lead coefficient is the lead number in front of the first term when written in standard form. So for that example, it's 2. Alright, this next one is not in standard form yet. So we're going to rearrange it so that the lead term for standard form is 2x to the fifth. That's the highest exponent. And then plus 6x squared plus x. So now I can see that the degree is a 5. Get my face out of the way. Oops. There we go, technology. Alright, so degree 5 is referred to as a quintic, which if you didn't know that until today, that's okay. Kind of makes sense though if you think about the prefix and stuff. Quintuplets, all that good stuff. Alright, coefficients of the lead term would be a 2. This next example is really funky because they don't use like pretty integer numbers anymore. Now they're using some irrational things, and that's okay. That doesn't change the way we do this problem. So standard form would be, let's see, the quadratic term would have to come first here. So f of x equals pi x squared, that's a fun coefficient. Let's see, minus 0.5x, and then minus the constant of square root of 2. So that is a degree dos, and that means it's called a quadratic. We know that from last semester. And then the lead coefficient in this problem is super fun. It's our friend pi. There you go. So a lot of vocab coming your way, but at least it's vocab that we might be slightly familiar with. All right, if I'm going to evaluate a function, we've done this many a times where we just use what's called direct substitution. This is what a lot of kids refer to as plugging in. That is not the official term. The official term is either evaluating a function or directly substituting a value into the function. So if this is your function, and you're going to, quote, plug in a 3, this is the name of what you're doing. This is like the command, if you will, and this is what you would either type in your calculator or do in your head. For Algebra 2, we're going to be typing that in a calculator, so don't panic. I'm not going to make you do that in your brain. So here's our function, f of x equals 3x minus 5. So this is the recipe. It says take 3 times your x value and then subtract 5. And then later on in the problem it says, why don't you go ahead and evaluate it at negative 4. We can do this in our head. This is negative 12 minus 5, which is a negative 17. Okay, our next function is our friend the absolute value function with a 3 out in front of it. So it says take your function, which is 3 times the absolute value of x minus 2, and then instead of using x, they want you to plug in a 1 for the x. So here you have to be a little careful because absolute values are pretty much the same thing as parentheses as far as like order of operations. So you have to do this part first, and you have to go inside the absolute value first. So 1 minus 2 is negative 1, but then you're going to take the absolute value of negative 1, which is 1. So 3 times 1 is 3. Kids always get that one wrong because they do order of operations incorrectly on it. All right, and then our friend the quadratic. Some of us learned this lesson the hard way. When you're plugging in a value, especially into a polynomial with exponents, like we have here, this negative 2 is going to mess up your problem if you don't use parentheses. So 4 times x squared plus 2 times x minus 1. Then if you place the negative 2 into all those parentheses, this is the part where a lot of us kept messing up last semester, where we weren't using parentheses and therefore we weren't getting the right answer. Order of operations says if you're doing this in your head, you'd have to do the exponent first. So negative 2 squared is going to give you a positive 4. So you have 4 times 4 in that first term. And then 2 times negative 2 is a minus 4. So I have 16 minus 4 minus 1, 11? Shouldn't make fun of you guys for messing up, but probably I just messed up. Let's see. Yeah, it's 11. We're good. There's another neat little feature that we can do on our calculator. It's called storing. So if you have a TI-84, 83, anything really, I'm going to show you what this looks like to store. It's kind of a neat feature. You can only do one number at a time though, so if you're storing more than one value, don't bother using this. But this is a neat little trick. Your calculator has a little button. It says stow. So in your home screen, right above the on key, it says stow with an arrow. That refers to storing values for variables. So what I'm going to do on that last question we just got done, I'm going to type the negative 2 first. And then I'm going to say, calculator, please store that as the variable x. And I use the variable key just because it's really easy to get to. You could also use the alpha keys that are in green on your screen, but then I have to hit like shift, alpha, and I don't want to do that. So right now my calculator thinks that while I'm in the home screen, anytime I press the x key, it's really pressing a negative 2. So I already forgot what that function was. It was 4x squared plus 2x minus 1. Okay, remember. So I can literally type that. 4x squared plus 2x. Not that. Plus 2x minus 1. And remember, my calculator thinks all the x's are negative 2s, so I don't have to use any extra parentheses. It knows that it's a number and it's going to square it properly. It does order of operations perfectly in a horizontal method. Done. So if you like that store feature, go ahead and use that. Again, only used for like single variable evaluation. This is a new topic for us, but this is a huge topic for Algebra 2. It's called end behavior. The end behavior of a polynomial is what's happening on the very, very, very far right side. So as x's approach infinity, that's a really fancy way of saying the very far right end of your polynomial. And then also to negative infinity, which would be the very far left side of your polynomial. So this looks really strange. You have two end behavior lines that we're going to work at filling out here. And this first one says, my function approaches something as my x's approach negative infinity. This is a very fancy way of saying as you look at the far left side. And then the other line of end behavior says the same thing, except now it says x's go to infinity, which is a very fancy way of saying right. So for now, I'm literally going to write the words left and right down. I'm also going to give myself a little sketch. And if you didn't know what the function for x looked like, it is a line. So it looks like this. So think about this as being a template. Every time I ask for end behavior, I have to write down this template. F of x approaches blank as x approaches negative infinity. That's the first end, and then I need the other end as well. F of x approaches blank as x goes to positive infinity. So I'm going to write the word left right here. I'm going to write the word right here. And then if I look at my little sketch here, if I'm a little bug and I'm traveling along the left side, it's going down, 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 down to infinity, to negative infinity, excuse me. And that's what I write in this first blank. And then if I go along the right side of my sketch, if I'm this little bug and I'm going to the right, traveling along it, it's going up, 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 approaching positive infinity. So that's what end behavior looks like for our polynomials. This is an upside down parabola, so it looks something like this, huh? I mean, not exactly like that. That was a really bad job. But so his end behavior, we're going to start off with the template of end behavior. Which this is always going to be the same for our polys. And frankly, for Algebra 2, we're always going to use this as our end behavior template. Things that don't have the template that matches this, we're just not going to do end behavior on this year. When you move on to pre-calc and Math 4 and Calc Algebra, you'll do other things. All right, so remember, x goes to negative infinity is a way of saying to the left. X goes to positive infinity is a way of saying to the right. So you're that little bug again. If you travel along the left side of your curve, you're going down to negative infinity. But if you travel along the right side of the curve, you're also going down to negative infinity. So you might have a case where both ends of your end behavior are heading in the same direction. And we'll talk more generally speaking about when that occurs and why it occurs. To bring back an old topic. Let's sketch this quadratic, and then let's also talk about domain and range. And you know what? While we're at it, we might as well just talk about end behavior. Why not? Without using your graphing calculator, we should probably be able to figure this out. This is a quadratic that's been shifted up 3. So instead of being at 0, 0, it's, up here. And then it opens upwards because it's got a value that's positive, and it just, if I want a real accurate graph, I'd get some points, but it's a parabola. Whatever. Let's talk about domain. This goes forever to the left and forever to the right. So remember, your domain is measuring exactly that. So his domain is negative infinity to positive infinity. But the range, remember, measures the bottom to the top, the lowest y value to the highest y value. And this guy has a range that begins at 3, but it does have a vertex at 3, so you please use an ordered bracket here. And then it goes up to infinity. So that's old concept of domain and range. Let's quickly talk about the end behavior for this function. So we're going to write out the template. Oops. Oh, I put that there. Parenthesis happy today. Okay. So I always do end behavior in the same order, so you'll notice I always do the left behavior on the first line and the right behavior on the second line. If you happen to switch that around, that's okay. You just got to be careful. So if I look at my sketch, over here on the left side, it's going up. We call that infinity. And then the function over here on the right side, also going up. We call that infinity. There you go, end behavior. Weird concept, right? Not too terrible. We've done worse things in Algebra 2, that's for sure. Alright, so this one, if I graphed this on my graphing calculator, because you guys are new to the quartic function, you probably don't really know what this looks like. 2x to the 4, 3x squared plus 1. Alright. You need to get this typed in. Get out the old function, though. I don't want that anymore. So I have 2x to the 4th plus 3x squared. I need to go back and check. I'm feeling like I screwed up this function. Ugh, goodness. 3x squared. 3x to the 3rd. See? I knew I messed it up. Go back. Alright. So now, if I graph this, it's it kind of resembles a quadratic, but it's got some extra wiggles in the middle. That's because it's a quartic, and that happens. So I don't really need you guys to do anything crazy other than I need you to transfer this over to your paper. And then when we go to answer domain and range, domain, easy. Negative infinity to positive infinity, because there are arrows over here. Your graphing calculator doesn't show you arrows, but it does go forever to the left and forever to the right. The range, however, we need to figure out how low this guy travels. So I have a feeling it starts at 0, but what I need to do is I need to find the minimum using my graphing calculator to make sure that it is indeed 0. So second trace, that command, you pull up the minimum finder, so number 3. Let me get this out of here real quick. And then it says left bound. Remember, you got to drag your cursor using your left arrow so that it's to the left of your little dip down here you're trying to find. So hit enter. And then it says go to the right of it, so drag your cursor to the right for a little bit. And then these two vertical lines that pop up should be like holding the minimum in between them. And when it says guess, you just hit enter one more time. So remember, oh, I'm glad I didn't just assume that was 0. It is not 0. If you look at, we're looking for range, remember. Range is the lowest y value to the highest y value. So this guy's range actually starts at, and we'll use a bracket because it does have a point, but we are going to have to round, negative 0.07 if we round that up to the hundredths, and then it goes up forever. So this is a good case of like, I thought it was 0 for a minimum for your range, but it really wasn't. So I'm glad we have the technology to figure that out. Where's my paper? There we go. So, let's see. I filled out domain on the other screen, but let's talk about end behavior because that's our new concept. So again, left and right end behavior are the two ends that I'm referring to. And let's see, I don't remember exactly what this looked like, but you know, something like this. I don't know. So over here on the left side, function's going up, up, up to infinity. And then on the right side, function's going up, up, up to infinity. It's a beautiful sketch by Mrs. Abruzzo. Alright, this next guy, I need some calculator assistance to see what it looks like. We just don't know enough about this yet in Algebra 2 to figure that out. So, oh boy, I'm going to pause the video, I'm going to get this typed in, and then get a graph of it. So I typed that function into y equals, and then I get this picture, and this is what we call a cubic polynomial. And like a quadratic goes either up, up, or down, down, depending on the coefficient, a cubic ends up going like this. So I would transfer this to my paper, and then I love the odd degree functions because when I'm asked for domain and range, they're just negative infinity to infinity. They go forever to the left and right, they go forever to the bottom and top. So domain and range are super easy for odd degree functions. The end behavior is not as exciting, or more exciting if you want to think of it that way. I still want left and right end behavior, but they're going to be going in opposite directions, so you have to be really careful, and then if you're dyslexic like me, you're going to have a tough time, so be careful. So this is the left behavior, so if I travel along the left side, we notice it's traveling downward, so we call that negative infinity, because it's going down. And then on the right side of your function, over here, I notice it's going upwards, so we call that positive infinity. So lots of old stuff coming back, lots of new vocabulary, and then a very large new concept of end behavior that we're going to see on every function that we get from here on. So happy graphing!